Right, welcome everybody. It's my great pleasure to now introduce our keynote speaker for this morning, Mihaela van der Schaar. Mihaela has more distinctions than I can enumerate right now, but let me just mention one to get going. She has an incredible 14 accepted papers at this NeurIPS 2021. And if the statistics are anything like last year, I believe this makes her the most prolific author at the world's top machine learning conference. And this is for a good reason, because Mihaela works on awesome topics such as automated machine learning, interpretability, and healthcare. And I'm super excited to hear her talk. So please, Mihaela, take it away.
Thank you very much, Frank, for the kind introduction and for inviting me here. Thank you and Marius very much for giving me this opportunity. When you said this introduction, I wonder whether you are going to say whether automated machine learning was at stake at generating the papers. But the reality is that the reason behind, let's say, the excitement we have in machine learning is due to the fact that medicine, which is the application area that we are looking at, is an enormously inspiring area, and it provides a lot of ability to think differently about machine learning, and I would say often creates new frontiers for machine learning. So today I'm going to talk about automated machine learning and how it can empower the revolution in healthcare. But also I'm going to talk at the end, if we have time, about interpretability, because we really cannot just provide in medicine and healthcare predictions or guidance, decision support without interpretability. I'd like to start by thanking my PhD students and postdocs, as well as the software engineers and communications managers that are involved in our research team. Without them, all the research you see here would not be possible, and they have greatly contributed to this research agenda. I always like to start with a motivation by Sir William Osler, the father of modern medicine. If it were not for the great variability between individuals, medicine might as well be a science, not an art. And indeed, it is our group's mission to develop machine learning methods to move medicine to science by delivering what I call bespoke medicine, which is one step further than what we currently think when we think about precision medicine. And I will talk briefly about that later. Understand the basis and trajectories of health and disease, empower healthcare professionals and patients, inform and improve clinical pathways, utilize better the healthcare resources, and even reduce costs, as well as transform population health and public health policy and enable new discoveries. AutoML plays a very important part in this ecosystem. And today I'm going to present to you a few aspects of how we have used automated machine learning in healthcare. If you are interested to read more about this topic, we have a little blog on our website dedicated to AutoML and its power in medicine. I'm saying this because some of you may prefer to read rather than just follow the various slides, or you may want to accompany these slides with some additional material, and this is a good place to start. But our group is not only working on AutoML, and while today I'm going to talk about AutoML, I want to tell you about what surrounds this ecosystem in order to enable transformation in healthcare. First is data, because without high quality data sets, we cannot do analytics and we cannot do AutoML. And unfortunately in medicine, it is very difficult to get high quality healthcare data. And this is understandable because such data has privacy concerns. This is our healthcare data. So one important dimension in this context is generating, using synthetic data, high quality and highly private synthetic data sets. So the area of synthetic data generation using machine learning, it's an important pillar of our research lab. And if you are interested to hear more about synthetic data and how can we generate synthetic data sets for using machine learning, which fulfill, again, high quality guarantees as well as privacy guarantees, please take a look at our ICML 2021 workshop dedicated to this area. We really need more researchers to be involved in this area of synthetic data. Then, on the basis of high quality data, we generate analytics. AutoML is an important component, and there are other dimensions to this. As you are going to see, AutoML is not only used for prediction, but also for causal inference, etc. Then we also want to issue interpretability associated with this. We try to interpret what the machine learning has found. So interpretability represents an important piece of the ecosystem, as well as uncertainty quantification. Can we issue predictions associated with them? Can we issue true coverage guarantees? Can we say when the machine learning model was confident and when it was not? And on the basis of this, both interpretability and uncertainty quantification, clinicians can decide whether they can trust the machine learning model or not. So they represent also an important part of this system. Finally, in recent times, we have started a new area in machine learning, which we call quantitative epistemology. And the focus here is to understand how humans, in our case, medical providers, but this could be more general, it could be any decision maker in a quantitative field, how they actually learn and make decisions. So we try to not only understand the black boxes and try to make them interpretable, but we also try nowadays to use machine learning to understand the gray cells, the black boxes of decision makers, such as clinicians, with the overall role of empowering them rather than replace them. So we hope that by understanding better how humans make decisions, how they integrate information and learn, and use machine learning to understand that, we can build better analytics and better systems in healthcare. But today I'm going to focus on AutoML. And since I'm going to highlight various areas from individualized treatment effect inference and causal inference to synthetic data, I'm going to briefly touch on some of these topics. If you are interested to hear more about these various topics, whether it is individualized treatment effect inference, synthetic data, machine learning for time series, or more generally, machine learning for healthcare, please take a look at our website where we have a few of these tutorials. Also, if you are interested to develop machine learning methods for healthcare, we have started around 1 year ago a set of engagement sessions online with machine learning students and professionals interested in this area. So if you are interested in the topic, please subscribe and join forces with us because we really need more researchers in machine learning to be involved in this area of medicine. Also, if you are interested to see how clinicians and medical professionals are using these tools and how do they think about these tools and what do they need to really practice better medicine, also you can see online another engagement session which is only open to clinicians but which is available online, and you can see what they are thinking about these various tools, inclusively tools in AutoML. So you can see their requirements and their thoughts. So please take a look at that. But now let's start to talk about what AutoML can do in medicine. As I mentioned, patients are complex and they have diverse genetic background, environmental exposures, lifestyles, histories, and interventions. And this translates into different risks, different competing risks potentially, variation in symptoms, health and disease trajectories, and responses to treatment. So what we are trying to do is to go beyond current precision medicine and personalized medicine, which often fits the patient to a pattern based on a single set of features, static set of features, most often based on genetic information. We would like to go beyond that and recognize that actually the patterns of the patient may change over time with age, with lifestyle, with onset of new conditions, as well as progress of a particular treatment. So what we would need is to adapt over time these changes in pattern and discover these changes in patterns that the patient is undergoing, and match the patient to the current pattern and issue on the basis of these forecasts. How can we do all that? Of course, using machine learning. So while the current focus of medicine is to assess risk often one at a time. So often the patient will go to the clinician with a particular set of symptoms, and this set of symptoms would often be assessed with respect to one risk at a time independently. Ideally, what we would like to do is we would like to monitor the patients over time using many risk scores for many clinical conditions and develop a holistic view of the patient health, not only based on the current symptoms and risks, but also other risks that the patient may develop over their lifetime. But this is challenging because we would need to issue risk prediction for many different clinical conditions and very diverse patients. And there is no one-size-fits-all solution. As you are going to see in a little bit, we will need to face the following challenge. We need to select a particular machine learning model for a particular data set as well as clinical condition. And that is challenging for data scientists using clinical data sets who may not be at the cutting edge of machine learning. Also, we need to accompany this clinical analytics with interpretability and explainability, trustworthiness, and also enable reproducibility. So let's think about machine learning in healthcare, especially in this simple setting of risk, and then I'm going to move beyond that. So we see often machine learning resulting in high predictive accuracy for some diseases. And also what is beautiful about machine learning is that we do not need to curate necessarily what data should be selected. The machine learning model can discover what information is relevant and do feature selection. And also we do not need to impose certain assumptions about how the variables will interact. But the challenge is to select a particular machine learning model, and the machine learning community is prolific, so determining what models to choose is complicated. Also selecting what hyperparameters to choose, and all of that would require extensive experience in data science. And to illustrate that, this is an example early on from our research where we chose 4 different data sets, all of them on cardiovascular disease, and compare the best machine learning model with the best clinical score and the best statistical state-of-the-art techniques, which are often based on Cox proportional hazard models. And what you see is that different models were best for different data sets, and how much better the machine learning models were depending on the specific data set. So there was no one-size-fits-all machine learning solution. It was not only a particular boosting algorithm or neural network, or even another machine learning model that may have been targeted to that particular data set. Different data sets require different solutions. So we would like to ideally predict in advance which method is best, and we would like to know how confident we are in it. And also we may want to look at different metrics of performance, not only at receiver operating curves, but also, for instance, C-index or the quality of well-being. And I will talk more about that a little bit later in this talk. So the challenge we would like to address here is that we have many diseases, many variables, many different needs for the clinical researchers, and also things may be changing over time, as is the case in COVID, where the population actually is changing over time, and we may have drift over time of the different data sets. So a brute force approach to machine learning may be prohibitively expensive and not very accurate. So instead, we would like to use AutoML to make machine learning do the crafting of machine learning models. However, as opposed to a lot of the wonderful work that happens in machine learning in AutoML, what's different in AutoML, as you are going to see in a little bit, is that we do not only need to do predictions. I'm going to start with predictions such that everything is familiar, but in a little bit you are going to see that we need to do also time to event analysis, competing risk, possibly complicated time series predictions, as well as causal inference for treatment effects. So this poses new problems to AutoML that go beyond some of the AutoML that happens in other areas besides medicine. Let me start with automating risk prediction, because this is an important issue in medicine. Because as I mentioned, we would like to issue risk prediction for a variety of diseases. And the challenge is that we have a huge design space to choose from. And the reason behind it is that we do not only need to issue risk prediction, we also need to deal with missing data as well as feature selection. So we need to determine entire pipelines following the data acquisition. So we need to do automated, if you like, selection of pipelines that encompass imputation, feature selection, prediction, as well as calibration. And this is indeed what we have done a few years back, where we created a tool for crafting such clinical scores, where we use data and build these pipelines or missing data imputation, feature selection, classification, and calibration. And we not only issue predictions, we also issue explanations associated with this, but more about that later. Also, we do not only issue one prediction associated with one pipeline, but we integrate using Ensemble's multiple such pipelines. And we are going to do that using a new Bayesian optimization approach that I'm going to show to you in a little bit. But let me also say that what's important here is to learn from other data sets as well. And here is where meta-learning is very important, because you would like to use priors and learn from other complementary data sets. This is an ongoing research agenda. What we have done in 2018 is relatively simplistic, and this agenda on how we can use other data sets or other models to empower the AutoML pipeline for a given data set still constitutes an important research agenda. That's an ongoing agenda. Sorry. Now, how do we really do this automated pipeline? We need to select algorithms at the different stages in the pipeline. We need to select hyperparameters for different algorithms, and we need to choose different algorithms at different stages of the pipeline. So this represents a complex combinatorial problem. And it is actually a vast combinatorial problem. And it's a challenging one because it's not only an optimization problem, it's a learning and optimization problem, because we cannot evaluate this utility function. So let's assume that we are interested in area under receiver operating curve. So we need to evaluate a particular utility function or loss function that is unknown for a new data set. So we need to learn and optimize at the same time. And this is a hard optimization problem. And it is prone to the curse of dimensionality. We often know that if we want to do Bayesian optimization in more than 10 dimensions, this is challenging. So just putting, for instance, a Gaussian process prior on the utility function, on the performance of the pipeline, and then doing new pipeline acquisition by evaluating where we have the most uncertainty and evaluating that particular pipeline, and in this way acquiring information about the performance of the pipeline is not going to work very effectively. What we have done, we have at the time developed something that we call structured kernel learning, which is able to learn correlated performance of algorithms. So here when we talk about correlation, this is actually metaphorically used. We are looking at the performance of different algorithms and correlated performance of these algorithms, and we are going to learn it for a new data set using this structured kernel learning. So for instance, here for illustration, we learned that these algorithms in red for this new data set are going to have a similar performance, and the one in blue is going to have a different performance. In this way, we can learn across a particular set of algorithms, which are grouped together for this data set, what parameters they should be sharing. So they are learning together the various hyperparameters and share information, while algorithms that are in different groups are not sharing this information. So this is a divide and conquer approach aimed at speeding up the performance of this Bayesian approach in this pipeline setting. So this represents a sparse additive Bayesian optimization technique that we have developed. And the structure of the kernel is unfortunately unknown a priori. So we do not know in advance what algorithms are going to have similar performance and which ones do not. So we are going to define a variable zi, which is an indicator of which subspace a particular algorithm belongs to. And you see here initially, all the algorithms are going to have priors associated with them. This could come from other data sets, or it could be just a Dirichlet prior. And what we are going to learn afterwards, as we are getting information about the different algorithms, is the posterior decomposition, to which particular subgroup is a set of pipelines belonging to. So as we are acquiring information, we are learning the subspace to which these classes of algorithms appertain, and in this way we learn effectively over time the performance of algorithms, and hence we learn how well they are going to do for this particular data set. It is on the basis of this that we also are able to estimate credible intervals, and hence the uncertainty of how well the algorithm will perform on this data set. And we are able to issue in this way predictions on the basis of ensembles, which are aggregated on the basis of this not only performance, but also the uncertainty associated with it. And this is important because these data sets are often not vast, so using predictions on the basis of a single pipeline would discard useful information. So this is why we often rely on these ensembles. And the post-hoc constructions of this ensemble is done, as I mentioned, using this Bayesian model averaging, using the posterior distribution of the performance as identified through these Bayesian optimization techniques. And the weight of every pipeline is just the empirical probability of it being the best for this data set. Now, we have used this autoprognosis framework in a variety of settings. For instance, in prostate cancer, in a variety of data sets related to complications in hip arterioplasty, in cardiovascular disease, but also in COVID-19, as well as in breast cancer. Most interestingly, early on in the pandemic, we worked closely with NHS Digital here in the UK and developed a machine learning model on the basis of this automated framework, automated machine learning framework, to help hospitals plan better resources for and beds that they should allocate for COVID-19 at a particular moment in time, given the current state of the pandemic. So what is interesting is that very, very early on in April 2020 already, we were able to deploy such a system together with NHS Digital. And the only reason this was possible was that we had automated frameworks like the autoprognosis that were able to be used out of the box. But what's interesting in medicine goes beyond prediction. So what I'm going to talk next is about survival models. I'm not going to talk about competing risks. I'm going though to talk about causal models and temporal models. So what is often interesting in medicine is not only to make a prediction at a fixed time horizon. So will this person develop cardiovascular disease or breast cancer in 3 years' time or 5 years' time, but rather to do time to event analysis to determine what is the probability of this patient to develop this disease over time. And what is interesting, if it is to look at the variety of statistical and machine learning models for survival analysis, you can see that there is no best survival model at all time horizons. It depends on the time horizon. And this you can see in here. So ideally, what you would like to do is to select the best model across the different time horizons. So this is illustrated here again with showing this C-index, which is often used, this concordance index that's used for estimating the performance of the survival models. And you see that different models at different time horizons are best. And what we would like to do using AutoML is to construct a valid survival function with good discriminative performance, which is the C-index, which is also well calibrated. And I'm going to talk about calibration in a little bit, because for that we are going to use a calibration method based on the Brier score. So what we would like to do is to develop these automated machine learning models for survival analysis, which will create ensembles over time with both discrimination and calibration performance that's of high, that's high. And hence what we would like to do is to estimate the risk function as shown in here, the survival function, the probability of the patient developing the event of interest, given the calibration being high. So what you see here is that the utility function is the survival function and the risk associated with this, but this is subject to a constraint. And this is the time-dependent Brier score, which is used for calibration in the statistical community. In the case we want to calibrate the data set to a particular the characteristics of the population on which we want to deploy this particular model. So this is now an optimization problem that's constraint optimization. And we are going to solve that using a constraint Bayesian optimization, and we are going to quilt patterns of models. Let me tell you why we call this a quilting survival model or survival quilts. As you can see here, we are going to quilt across different models a temporal quilt, which is going to aggregate the different models at different time horizons with different weights. And unlike in the previous example, where we could simply switch between models easily and aggregate model easily using Bayesian model averaging, here it's more complex because at the different times, we need to make sure that the survival function remains monotonic. So we cannot just in an ad hoc way quilt the different models. We need to maintain the ability of the quilting pattern to fulfill the properties of survival models and their monotonicity. So the challenge when we deal with this Bayesian optimization in the survival setting is to quilt models using Bayesian optimization in such a way that the weights are selected over time by constructing a survival valid risk function. And what's important here is that we carry forward to future time horizons a consistent risk function, such that this risk function doesn't go up and down. Then a second challenge that I'm going to illustrate a little bit later in the next slide is the fact that we need to solve a constraint optimization, as I mentioned. So we need to do Bayesian optimization given constraints, and the constraints are coming from the Brier score. Finally, we need to make robust this optimization. So we need to make sure that we select these time horizons at which we weigh differently the different models endogenously. So we do not only determine, okay, every 1 year I'm going to change the model. The time at which the model should be changed depends on its performance. So we need to have endogenous time horizons. So we need to iterate actually across this entire constraint Bayesian optimization and select the time horizons at which we are changing these quilting patterns. As I mentioned, this is a constraint optimization. So this is a black box optimization, but one where we not can just easily, let's say, put GP priors and then solve Bayesian optimization. We need to have an augmented Lagrangian Bayesian optimization in this case that considers the constraint associated, that's highlighted here in green, that's associated with the calibration function. And this is best illustrated in this figure here. So unlike in a conventional setting where we would have, for instance, a Lagrangian optimization that we are going to solve, and every time, let's say, we are going to have a minimum that is attained, we can declare success. Now we also have a constraint, and the constraint comes from this particular, let's say, Brier score. The Brier score needs to be below a particular threshold. And this is indicated here through this red line. And what you can see is that the first two minima that we have, which are highlighted with this yellow star, are actually not fulfilling the constraints associated with our Brier score. It is only the third time where we are actually able to achieve this particular constraint, so we can declare success and we can find the survival function that is not only of high performance in terms of C-index, but also in terms of this calibration score. Also, what is interesting to see is that in this way, we are able to quilt patterns that are superior to every particular function for a variety of data sets. So now we have this ability to select among the models at different time horizons and issue using AutoML these predictions over time. Also, you can see that these quilts may be different across different data sets, and the performance gains may be different depending on the data sets. But what is nice about AutoML is that it can select the best model. And this best model may be different again across the. Also is important, as I mentioned before, to realize that different times may require different quilts to be changing at different horizons. So this endogeneity of the survival quilts, where we do not determine exogenous every fixed periods, but rather endogenously determine the time to switch the quilt, leads to additional performance improvement. Let us now go beyond just predictions into treatment effect recommendations. So we have a treatment, we have Bob who has been diagnosed with a particular disease, and we would like to determine for Bob, given their unique characteristics, what treatment we should be using. So this is a causal effect inference problem or a treatment effect inference problem. And the challenge here is that we really need to learn on the basis of data that does not contain counterfactuals. So we only observe what has happened to the patient given the choice of treatment made. So if the patient was treated, we observe what happened to them if they are treated, but not what would have happened to them if they were not treated. So unlike in the previous two examples where we can use cross-validation, for instance, to select models, we cannot do that here. So we do not have explicit labels. And this is the big challenge of the causal inference literature. This also poses additional challenges, which I'm not going to talk too much about here, but need to be solved and addressed, that we often need to learn from biased data because we only observe the data that is collected on the basis of the biases of the clinicians. So often we don't learn from randomized control trials, but rather from observational data, which is biased on the basis of the clinical practice. And a challenge here is, if you want to do AutoML, is that we will need to learn on the basis of this observational data. And indeed, if you look at the literature in this area has flourished in the last couple of years, and it contains results from machine learning, from statistics, from econometrics. And you see many different types of models appearing in this area. So AutoML would be a natural choice to select models for different data sets. But the challenge is that we cannot select the best model easily using cross-validation. And again, this is not possible easily because we cannot observe the counterfactuals. So ideally, what we would like to do is to be able to develop a framework that can learn on the basis of only factual data and select what model is best for this new data set in terms of causal inference. So this is a problem that we tackled a few years back, and we built a model for automating causal inference by dealing with the core issue associated with this. How can we validate causal models without observing the causal effects, only observing the factual data? The error metric or the loss that is often used in these causal inference papers is called PEHE, or precision in estimating heterogeneous effects. And this is actually a mean square error of a causal model between the actual treatment effect and the estimated treatment effect. And the treatment effect is this difference between the treated outcome and the untreated outcome. And as I mentioned, we would like to estimate conditional average treatment effects or individualized treatment effects, which are depending on the patient features X. So you see here, for instance, two patients, and we would like to estimate for them whether it is better to treat them or not. And what you see is that, for instance, the woman who is the younger patient would do better if it was not treated, and the older patient would do better if he was treated. However, in the observational data set, we only observe the decision that was made, and that's indicated by a blue dot. So the younger patient indeed was not treated, and the older patient was indeed treated. But we would like to estimate how much better would have been if we would have treated them differently. And this is the type of problem we would try to estimate from observational data. And then for new patients, we would try to estimate that prospectively. But this is challenging because, as I mentioned, we do not observe this counterfactual. So the idea we had is to use some very simple insight. And this insight comes from the Taylor series approximation, which we know from high school, where we know that the value of a function at a given point, the given input, can be predicted using its value at a proximal point. And in this way, we can estimate at this point at which we do not observe the data, how well the function, in this case, the treatment effect, would have been. So we use data we have, and we estimate this approximation of the treatment effect at a proximal point. But unfortunately, we cannot just use Taylor series approximation in this case, because causal inference is actually not a function, is a function of a function. So we need to use functionals here. So in an analogy with the Taylor series, we are estimating the performance of a causal inference model as a functional of the data generating distribution. So what we use is we use the true distribution and estimate counterfactuals using this approach. And how we are going to do that is by using the distributional analog of the Taylor expansion, using influence functions, which are, if you like, the functional analog of the derivatives that we are using in Taylor expansions. In this way, we use influence functions, which are able to generate, if you like, these derivatives of the causal inference models at the proximal data point. So in this way, we are synthesizing these counterfactuals. So we are going to have in the first step a plugin estimation, where we are using the plugin model and estimating the plugin PEHE mean square error loss. And then we are going to do bias correction, because we are dealing actually with information that is determined, again, at a proximal point. In this way, we can estimate Taylor approximations of different orders. Here is just shown a first order approximation, where we are estimating this true distribution, which is not accessible, it's not available in the data set, on the basis of these accessible empirical measures that are available in the data set, by doing plugin estimation, as well as estimating this first order approximation using the influence function. In this way, now we have the counterfactuals, and hence we can do a conventional AutoML. And what's interesting here is that the value of AutoML in this setting is huge, because there is no single machine learning model for estimating causal inference which is best for all data sets. What you can see is that if we take the 77 data sets that were used in the Atlantic competition, causal inference competition done a few years back, you see that any specific method is not better more than 15–17% of the time. Different methods are best for different data sets. And what is nice is that now, using automated machine learning based on influence functions, we can select the best model a priori 72% of the time. So by just looking at these various data sets, we can estimate and predict in advance which model would be best. If you want to read more about this agenda, you can look at our website dedicated to causal inference. And as I mentioned, this is quite short. If you want to learn more about causal inference for estimating individualized treatment effects, we have a quite comprehensive tutorial given by a few of my students and myself, going into in-depth description of all these different areas. Let me now talk about another topic, time series, because that's very important in medicine. We want to learn on the basis of a variety of time series data. And in healthcare, we don't only want to issue predictions. We want to do, again, time to event analysis over time, survival analysis over time, treatment effects over time, monitoring and screening, as well as clustering. And again, if you want to hear more about time series in healthcare, you can see some of the research pillars and some of discussion, some blog that we have about this on our website. Today, I'm going to talk about one key challenge in doing time series forecasting in healthcare. And that is, if we want to aggregate across the different machine learning models, whether this is different types of LSTMs or different types of encoder-decoder methods or different types of attention mechanisms, we need to select models that are good not only at one particular moment in time, but they remain good over time. So they are able to issue predictions that are accurate over time. And this is challenging due to the temporal distributional shifts available or present in the data. So for that, we would like to do what we call stepwise model selection. At different moments in time, we may want to choose different models, or if we use ensembles, we may want to weight different models differently over time. And this is a topic that we have explored a few years back in our work on stepwise model selection for sequence prediction. Let me tell you about some of the challenges associated with that. The challenge resided from the fact, again, that we needed to do Bayesian optimization for model selection, and for time series, this was very challenging. And the reason this is challenging is, as I mentioned, we want to issue predictions across time. So you see here different observations being made over time. So observation 1, observation 2, observation T, this could be vectors of observation, so we can have a multivariate time series data. And what we would like is to understand what model we should be choosing at these different moments in time to issue predictions over time beyond the current time step. And for that, we are treating actually each time step as its own black box optimization. And if indeed we would do that, the model performance at each time step would actually lead to a particular evaluation of a black box function. And because we have T black box functions to evaluate, this would lead to a multi-objective across the time horizon T Bayesian optimization. The challenge associated with that is that this is, of course, going to be very expensive. And as the time horizons are going to grow, this is going to become intractable. So are there other solutions possible? A solution that we envisioned was to do multitask Bayesian optimization, where at every time step, we are using past time steps to do warm start. So this becomes almost like a multitask approach where previous time steps are feeding the current Bayesian optimization at the current moment in time. And this would lead to transfer from previous optimizations to the current time. The advantage of this approach is that it requires evaluating the different deep learning models on large data sets, and this is really quite complex. And solving these separate Bayesian optimization procedures, even though we do multitask, but allocating this, let's say, this complexity of evaluation across these different subproblems is complicated. I'm not saying that this is impossible, but it is really complicated, and we were not able to figure out how to do that effectively. And also, we were not able to take full advantage of information from all the acquisition functions across the different time horizons. So instead, what we did is we solved this problem by jointly and efficiently learning and exploiting correlations across the different black box optimizations using a deep kernel learning approach. So what we have done, we have developed a deep kernel learning method for this stepwise model selection. So the key idea was to use this deep kernel learning to create feature maps that are measuring the similarities between the different data tuples in the time series setting. So as a first step, we can use machine learning models such as RNNs to learn embeddings. And then what we are going to do is we are going to use this deep sets approach to learn invariant representations. And subsequently, we are using these representations and mapping on the basis of the available data using the deep sets into the parameters and to the hyperparameters of the machine learning models using a multi-layer perceptron. So the 3 steps are first creating an embedding using a recurrent neural network, then obtaining a permutation invariant embedding using deep sets. And this is important because we would like to be invariant to the different sizes of the different time series data sets on the basis of which we learn. And we generate finally this feature map using a multi-layer perceptron. And this is what is used to determine what hyperparameters to choose and what models to choose from the vast number of models that can be used in the time series setting. In this way, we are able to show that this model selection over time is able in an automatic way to select models and is doing better than just handcrafted features done by experts. However, what we would like to also do is we would like to go beyond just building these models. We would like to build demonstrators and validate them together with clinicians. So we would like to be able to go through the entire pipeline all the way to deployment. So not only do conception and modeling and validation, but also building demonstrators. We have built a toolkit that is available for you to use that we call Clairvoyance, which contains a variety of the models that I described previously, both time series prediction, causal inference, as well as personalized monitoring. And the pipeline is really aimed at easy integration of new models as well as AutoML models. Because in machine learning for healthcare, we didn't have prior to Clairvoyance a basis on the basis of which we can enhance each other models and an open source solution where many of these models for healthcare could be benchmarked, compared upon, and aggregated. If you want to see how we have done that and how we have built a demonstrator on the basis of Clairvoyance and how we have debugged it together with clinicians, please take a look at our October session dedicated to these discussions with clinicians called Revolutionizing Healthcare.